Okay, let's take a look at the first question. The mean citywide exam score for a population of first-year high school students is 600. The standard deviation of scores for this population is 100. So we know sigma here. We know the population standard deviation. So we're going to use the z-score, and we're going to use standard deviation 100, and investigate, which is the test of mean. First-year psychology majors significantly different than the mean score of the population. Mean score, the mean of a sample of 100 randomly selected first-year psychology majors is 624. So we're assuming that the standard deviation is the same for the two groups. So the mean of the sample, in fact, we didn't give you the standard deviation of the sample at all, so you got no choice but to use it. Okay, so the mean of a sample of 100 is 624. So state your null and alternative hypothesis. Well, that's pretty easy, right? The mean of we want to the mean of x bar is 624. We want to see if that's different than 600. So we want to show that mu, the mean for psychology majors, right, is equal to 600. That's our null hypothesis. And the mean of the psychology majors is not equal to 600, is different from 600, significantly different. Doesn't say anything about bigger or smaller. So we're starting with the assumption that psychology majors have the same mean as everybody else, 600. So you can either put it this way: mean of psychology majors equals the mean of all students, or the mean of psychology majors is equal to 600, which we know to be the mean of all students. The alternative hypothesis, the mean of psychology majors does not equal 600, or the mean of psychology majors does not equal the mean of all students, which again, we know 600. It's the same thing. Calculate the value of standard error for the means of the sample size 100. Well, we know that the standard deviation is 100. Sigma over a square root of n is our standard error. So 100 divided by the square root of 100 is 100 over 10. So the standard error is going to be 10. Okay. Next, calculate the value of the t-score. You choose which is, or z-score, you choose which is appropriate. Okay, we're going to use the there's stuff going, there's comments going on that I haven't seen yet, so I'll catch up with them in a minute. Calculate the value of the t-score or z-score. Well, we're gonna work with the z-scores, right? Because we know that we know the population standard deviation, so we're working with the z-score. So calculate the volume of the z-score, which is appropriate based on whether or not the population is that. Okay, so let's calculate the z-score. So the z-score is going to be equal to the difference between the two means, x bar minus mu. That's 624 minus 600, which is 24, divided by the standard error, which is, we just calculated to be 10. 24 divided by 10 is 2.4. So our z-score is 2.4. Good, very good. Okay, so now calculate the p-value for this hypothesis test. And it's a two-sided test. So I'm going to actually get the table up here, z-table. Okay, so that we understand this, because I know you guys have a little bit of an issue with it's one-sided and two-sided. Okay, here we go. Here's the z-table, and I can actually use either side, right? 2.40 is 0.082, right? This is 0.082 is the tail that's represented outside a value of 2.4. If you did the plus, it would have given you a value of 98.18. In other words, the opposite of that. In other words, it would have been 0.008 to the right of that. So it's 0.008 to the left of the low end and 0.008 to the right at the high end. So we would double the 0.008 because we're counting the tail on the left side and the tail on the right side. We know that this result is 2.4 z-scores away from the mean. In this, it happened to be on the right side, right? But it could have equally been on the left side because we were only testing if they're different. So if we get a score of 0.008, we would say the p-value, the probability of being wrong, is 2 times 0.008 or 0.016. Okay, get that? Does that make sense? See why I'm doubling that? You got the right number. Salida, understand that you got the area, you got the right area, but we're interested in how far away from the mean is it, right? So it's a part of that tail that's outside of that area. So for you, it would have been 0.08 also, right? And then you double it because you want to accommodate both tails. If you're only doing a one tail test, you don't have to double it. We can use the Z table if you know the population standard deviation. We knew the population standard deviation in this case. We can also cheat and use the Z table if we have a large sample size, right? Now, technically, in practice, a lot of people in statistics, especially on initial analysis, might assume anything over a sample size of 30 is a large sample, even though it don't sound like a very large sample, right? I mean, statistically, it's a pretty big sample. Because once you get past the sample size of 30, the t-score and the z-score are not that different. Like in this situation, the critical t-value, the critical z-value for 5% was 1.98. For a sample of a size 100, the critical t-value, 1.96 rather, critical t-value might have been 2.01. Not much difference, right? In fact, we would have, either way, we would have rejected the null hypothesis. So a lot of people would say 30, over 30, you can get away with it. But keep in mind, technically, the right answer, if you don't know the population standard deviation, the right answer is to use the t-score, not the z-score. And you'll notice that SPSS always calculates the t-score. You never see it say z-score. It always calculates the t-score because it says, because it's a machine and it's no effort for it. Okay, calculate. Let's go here to 6. Choose the correct t-score for calculations. Choose the correct t-score for calculations involving a sample of size 23. Use the t-table of distribution 22 degrees of freedom. In other words, t alpha over 2 equals 0.025. In other words, alpha over 2 is 5%. In other words, 5% level of error, right? And degrees of freedom is equal to 22. So let's take a look at our t-table. So our t-table, okay, let me see if I can't get to it. Here's our t-table. Okay, so how many degrees of freedom was it? Degrees of freedom was 22. Sample size is 23. 22 degrees of freedom. Now, which column are we going to use? We're going to use the column which has a right tail, a one-tail probability of 0.025. In other words, 5%, an alpha of 5%. Little tricky, the nomenclature there, right? So it's going to be, the right answer to that is going to be, let's say sample size 20, 22. 2.074 is going to be the right answer to that. 2.053 is going to be the value, let's say closest value of t, like if you had the z-score or something like that. But the value, we're interested in what's the t value, what's the critical value of t for a sample size of 23 if we're dealing with a two-sided alpha equals 0.05 in a two-sided test. In other words, alpha over 2 is 2.5%. Alpha over 2 is 2.5% means alpha is 5%. Okay, it's a little confusing, a little bit tricky, right? So the negative value is negative 2.07, whatever it was, and the positive value is plus 2.07, right? Those are the two critical values. You can be below the negative 2.7 or above the positive 2.7. Doesn't say anything about asking you for probabilities, only for the t-value, critical t-value. Repeating the previous question using a z-distribution. If the population upper, what's the upper positive? Well, z-distribution for 5% chance of error. Two tail, 2.5% on each side. Alpha over 2 is 2.5, 2.5%. But out that makes alpha is 5%. That would be 1.96. That would be the 1.96 that we've long heard tell about. Okay? Okay, an article reports that diastolic blood pressure in all healthy adults is 78 with a standard deviation, doesn't say anything about the population, but a standard deviation of 6 milligrams of mercury, 6 millimeters of mercury. Assuming that diastolic blood pressure is normally distributed in this population, it's actually only giving you information about the population. Assuming that blood pressure is normally distributed, what percentage of individuals are expected to have values between 78 plus or minus 12 milligrams of mercury? Well, standard deviation it's asking about a population. This is not even a sample. There's no sample involved here. So we're just looking at the number. The z-score is just the number of standard deviations over the difference over the standard deviation. In other words, 12 over 6. It's two standard deviations apart. 12 millimeters below 78 is 2 standard deviations below. In other words, z is 2 below, z is 2 above. Well, we know 95% of the values are between these two. Okay, so we would expect 95% of the people in this study. It's kind of like a slip-in from what we did before, right? Just the population. So the right answer there would be 95%, right? Had this been 2.5 standard deviations on either side, so like maybe it would have been 15, plus or minus 15, then it would have been 99%, closer to 2.58. Okay. Now, suppose that a study had reported the mean diastolic blood pressure of a sample of healthy adults. Sample is 80 with a standard error of 1 millimeter of mercury. They already give you the standard error. Assuming that the diastolic pressure is normally distributed, what percentage of the individuals in this population are expected to have values between 78 plus or minus 2 milligrams of mercury? Previous question provides standard deviation, where this question provides the standard error of the mean. Okay, let me think about this. Let's see. I need to know how many standard deviations apart these two groups are. Okay, and and this time it's a sample, right? So in order to, let me think about this standard error. Let's see, what percentage is standard error? Is 1 plus or minus. Anybody got a guess there? Oh, I'm sorry. I didn't realize that. I got my sound turned off. So if there are some late arrivers, I don't notice that. So they should be muted now. Okay. Let me go back over this. Oh, there's a cat. I missed that. I like cats. Oh, excuse me. I have a cat here. Who's cat indoors? That's like I said, that's why I mute everybody, because if you can imagine, right now there's like 22 of us online together. If you can imagine what a cacophony it would be, when all this is going on. It's a little embarrassing too when you do that. So I wouldn't admit it was me either if it was me. So at any rate, previous question: in this population, expected to have values. What percentage of individuals in this population? And we have a sample that is 80 and a standard error of 1. Well, I don't know. My problem here is I don't know what the sample size is here, do I? Right? So what do you think I should do here? Anybody have an opinion on this? Question 10? Do I have an opinion on what the answer to question 10 is? No one? Yeah, I would say not enough info either. We don't know what the sample size is, right? Because we need the sample size. Okay, so I'm going to go to 11. In a air pollution study, Environmental Protection Agency technician obtains a mean of 2.34. I promise not to use any EOH. There are probably almost no EOHS majors in this class. I promise not to use a EOHS example. I use some more public health stuff on the test. Obtains a mean of 2.34 micrograms of suspended benzene soluble matter. That means soot. 2.34 micrograms of soot per cubic meter with a standard deviation of 0.48 micrograms for a sample size of 9. This is strictly a sample. The sample has 9 samples, has a mean of 2.34, and has a standard deviation of 0.48. Assuming that the population sample is normal, construct a 95% confidence interval. Right. So now we're dealing with something that involves a confidence interval, but we need to use T instead of using Z. So our mean is 2.34. We know that for starters. So it's going to be 2.34 plus or minus. If it was a very large sample size and we knew the population standard deviation, we might have said plus or minus 1.96 times the standard error, but we can't. We have to use a t-score that's appropriate for a sample size of 9, or in other words, 8 degrees of freedom. We're going to have to look that up. But before we do that, what's our standard error? Well, our standard error is the standard deviation. Since all we got is the standard deviation, instead of sigma, standard deviation divided by the square root of the sample size, 0.48 divided by 3. Okay, so that would be 0.48 divided by 3 is 0.16, I think. Does that sound right? No, it doesn't. 0.3, then 18 left over. 18 roughly 0.66, something like that, roughly 0.66. Okay, and so that's going to standard error is going to be 0.66. So it's going to be 2.34 plus or minus the value of t for this number of degrees of freedom times 0.66. So let's look up our t table. Okay, in our t table, here's our t table. For 5% error, 5% alpha, in other words, 95% certainty. Right-tailed and left-tailed each is 0.025. You add them together, you get your 5% for your 95% confidence interval. 8 degrees of freedom, so 2.306. So it would be 2.306 times our 0.66. Okay, and you add that, subtract that to get the lower bound. You add that to get the upper bound. I'm 1.16. I'm sorry, 0.16. So I'll put this up with all the answers later on, so you can actually see the actual answers. Okay, a regulator wishes to test the mean pollution level is different than the allowable upper level of 3.0. So what's our null hypothesis here? Our null hypothesis is that the average pollution level in this environment is the same as the limit of 3.0. And our alternative hypothesis is that the average pollution for this population, for all of the samples you could take here, is different than 3.0. We could make this kind of a one-sided result, but we don't really know that it's greater or less than, or it could be either. So this is a single sample t-test. How do we do a single sample t-test? We take the mean x bar, we subtract the mean of the population, or the test value, in the case 3. So 2.34 minus 3, that leaves 0.66, I guess, 0.66, and divide that by the standard error. And what did we say the standard error here was? It was 0.16, so it'd be 0.66 divided by 0.16, right? And that would give us a value of roughly 3 or so. I got a question. So it's 2.06 times. Oh, I'm getting some. Oh, I got some. There's some confusion. Let me actually do it on paper since there's some confusion about that last problem. Okay. Let's see. Let me get it. Let me just scroll back here a little bit so I can see the original problem. Let me get this thing out of the way. Let me get this thing out of the way. This thing out of the way. I'm so I can't get back to my notepad. Okay, let me get a new page. Okay, so let me get my data here. Okay, so x bar is equal to 2.34. Okay, mu, the value that I'm testing it against, is 3.0. We'll worry about that later. We're not doing that right now. X is 3. And the standard deviation is 0.48. And the sample size is equal to 9. So I'm going to do my confidence interval first. Okay, so my confidence interval is going to be x bar plus or minus the value of t for alpha is equal to 0.05, right? Value of t that I need for 9 degrees, for 8 degrees of freedom, times my standard error. So this is going to be equal to, let me move this up a little bit. Oops, move this up just a hair so you can see it. This is going to be equal to 2.34 plus or minus, well, this value of t turned out to be, so we can't get it back here, t table, put it out here. For 8 degrees of freedom, it turned out to be 2.306 plus or minus 2.306, right? If we had known the population, if this had been the population standard deviation, sigma, we would have used 1.96 there. But that's our punishment for using a small sample size, times the standard error. Our standard error is going to be equal to the standard deviation. We don't know sigma, so that's all we can use, over the square root of the sample size, over square root of 9. So that's going to be 0.48 over 3. Okay, and that's equal to 0.1. That goes in as 30, 18. 3 into 18 is 6.16. Actually comes out nice and round. Okay, so that's our standard error. Okay, times 0.16. So then I get my calculator out, and I'd say, okay, 2.306 times 0.16 is equal to 0.36, 0.37 roughly. I'm going to put that into memory for the time being. So this whole thing comes out to be, let me move this down here, so I can get it back. This whole thing comes out to be, I forgot it already, 0.36. So it comes out to be 2.34 plus or minus 0.36, right? So it's going to come out to be roughly 1.98 to, I'm going to add it to the other side, 2.7, right? Roughly something like that. Okay, so if we all agree with that, right, that's our confidence interval. Just so for our purposes right now, I'm going to notice that, my 95% confidence interval for the true mean for this area that I'm sampling excludes the 3.0. So I'm thinking in the back of my head, then if I do a hypothesis test on this, I might be able to reject my hypothesis that these two areas or this value is different than what we're exposed to in this area, okay, on the average. So let's do that part of the problem now. Okay, so if we do that part of the problem now, get a new page. Okay, this time our null hypothesis is, equal to mu for our experimental area where we're doing our experiment is equal to 3.0. It's the same as the regulated area regulation. And our alternative hypothesis, mu, is different than 3.0. We're not speculating at this stage whether it's greater or less than right now. We're going to do a two-cal test. Okay, so now the way I resolve this, I say, okay, I need to find out how many standard deviations, how many standard errors apart these two groups, these two values are. So t is going to be equal to x bar minus mu. In this case, mu is actually a value for the regulatory value of 3 over the standard error. Okay, well, that's going to be equal to 2. I wish my memory was better. 2.34 minus 3 divided by the standard error. And the standard error, was that 0.16 the standard error? Am I right about that? 0.16. So that's going to be equal to 0.66, negative 0.66 over 0.16. So that's going to be equal to, let's see, 4 times that. 4, 64, about 4 point something, right? That sound right to everybody? Sound good? T-score is going to be 4 something, right? Well, now I have to decide, is that 4, I'm going to call it 4 point, what was it, 4.125? Okay, I'm going to call it 4.125. Is my t-score for the difference between these two big enough to reject my null hypothesis? Well, I have to check to see if it's big enough by checking what for 8 degrees of freedom, right? I have to check whether or not this is bigger than the critical value. Well, we looked it up on the last problem. The critical value for T critical was something like is equal to 2.3 something, 3.07 or something like that, right? So I know I've exceeded the critical value, so I can reject my null hypothesis and accept my alternative hypothesis, right? So had this been a z-score, had we known the population, I could have gotten a z-score of 4.17. I could have actually calculated the real p-value by looking for the tiny little tip of the tail that would represent a z-score of 4.17. It'd be really small. It'd be like 0.0001 or something like that, right? But since we're doing a t-test and we can only do it from manually, can only do it from the table, unlike when we do it in SPSS and it calculates it for us, well, then I'm happy enough just to say that it's greater than the critical value, so I can reject the null hypothesis. Okay, let me pick up where I left off here. And where did it go? Where did all this stuff go? It's getting crowded here. Oh, I must have closed it. Jeez, where it closed? Open. Oh, it's a PDF file. That's why I can't find it. Here it is right here. Okay. We got through that. We got through that. Got through that. Ba-ba-ba. If the regulator tested if the mean of sample, oh, now this is a little bit different. Question 14, we can reject the null hypothesis at the alpha level equals 0.05 because we exceeded our t-value for that. If the regulator had tested if the mean of the sample levels were less than the average for all urban areas, one-sided test, would the null hypothesis one-sided test be rejected at a confidence level of 0.05? Let me see. So my t-score was 4 point whatever, right? So now, what is a one-sided test? What's a t-score, critical t-score for a one-sided test of 0.05? Well, if I get my t-table back, here's my t-table back again. If I get my t-table back, right? Now, if I want to do a one-sided test, a two-sided test at an alpha of 5%, in other words, 95% confidence, would have had a right tail value of 0.05. Well, now I'm only going to test one side of this possibility. I'm going to assume it can only be greater than, only be less than. So if I do a one-sided test, all of my 5% is on my is in one tail, either the right tail or the left tail. So I use this column instead of using this column. See, if we do a two-tail test, half of our alpha 5% has to be in the right or the left tail. So I have to use the 2.5% one. That's why 2.5 the right tail probability corresponds with 95% confidence. If I'm doing a one-tail test, all 5% can be on one side. So I'm going to use the same column I would use for a 90% confidence interval. Confidence interval is always two-sided. So this one also represents 5% on one side, 5% on the other side, which is 10% alpha, which is for a two-sided test, which is 90% confidence interval, right? So that's a mouthful, but if you just look at this, you should be okay. So it's 5%. So 8 degrees of freedom. The t-value I have to exceed is 1.86. In fact, it's a less rigorous test. If we were able to reject it for question 15, we're definitely going to be able to reject it for 14. We're definitely able to reject it for question 15 because a one-sided test by nature, you need to exceed a smaller t-score, and it's easier to do. So we reject it also. Okay. I think the homework had number 14. Correct answer is no. Is that the case? I have to check that. Because it should be yes, right? Everybody agrees it should be yes. Don't we all agree it should be yes? I think so. Yeah, it should. Well, whatever it says, both of them should be yes. Okay, we have a consensus. That doesn't matter if we're right or not. We have a consensus. Okay, so let's look at question 16. On what percentage of days would the observed pollution level be expected to exceed the allowable limit of 3.0? Use the mean and standard deviation in this Sample assumed that is drawn from a normal distribution. Well, we're stuck here. We only have the sample, and we're not going to use standard error because that's for samples. We're going to use the standard deviation. So, how far away, how many standard deviations away is 3.0 from 2. Where was it? 2.34. 2.34, right, minus 3.0 was a difference of 0.66 divided by the standard deviation. Standard deviation was 0.48, so 0.66 divided by 0.66 divided by 0.48, right? Well, that value 3.0 is 1.375 standard deviations away from the mean, right? So if we go to our Z table, because we're dealing with a population, we go to our Z table, it'll give us the percentage of time that we would be above a t-score of 1.37. Okay, 1.375. Z table. Actually, I should have it. I don't know if I have it open or not. Okay, should be able to get to it from here. Z table. Where is it? Where is it? Where is it? Come on. Come up to the front. That is over there. I can't get to it. There it is. Okay, Z table. And the value is, we're looking at the tail, so it doesn't matter if I use the top end or the bottom end, right? And it was 1.375. 1.375 would give us 0, 1, 2, 1.37. 0, 1, 2, 3, 4, 5, 6, 7. Somewhere between these two values, which is roughly about 8.4%, 8.45, something like that. Well, it was negative, but I'm using, and I'm saying it doesn't matter if I use I'm looking for the tail, the percentage of the population, percentage of the values in the population that will be above 3.0. Okay, and so it doesn't, since it's the normal distribution is symmetrical. I'm looking for the area in the tail. So it doesn't matter if I use 1.375 to look at the lower tail or plus 1.375 to look at the upper tail, because if I look at the upper tail, I'm gonna get that this is the area from here down. So the area that's left is that subtracted from 1, which is 0.08. If I look at the lower tail, I'm just going to get that area over there, which is also 0.08. So it doesn't matter which way I get it, just as long as I remember that the area I'm looking for is the part in the tail, not the part in the middle. Okay, so that's what we get for that one. Okay, percentage of days. Okay, William Gossett. Remember who William Gossett is, right? That's the guy, that's student. Makes 5 independent measures of alcohol content of a batch of beer. In percentages, the values are 5.4, 4.8, 5.1, 6.2, 5.2. This is just simple sample of size 5. Do these measurements provide sufficient evidence to reject the null hypothesis that the mean is equal to the mean for all batches made this way are equal to 4.5 at a level of confidence of 0.05? But we're going to have to actually work that out, aren't we? I'm going to use Excel to do that. I'll get a new workbook. Okay, I'm going to keep you guys just a little bit later since I know this is an issue with us. Okay, so let me get this out of the way. So let's get these numbers down here. 5.4, 4.8, 5.1, 6.0, oops, 6.0, 5.2. Okay, so I know my sample size is 5, right? So first thing I know is n, okay, is equal to 5. Second thing I know is going to be my average, my mean of the sample, x bar. Going to be equal to the average for all of these numbers. Next thing I know is my standard deviation for my sample. Okay, it's going to be 0.44. So now I want to test the null hypothesis that the x bar, the population that's represented by x bar, the mean for the entire group, is going to be equal to 4.5 or different from 4.5. Okay, let's give that a test. Let's test that. Okay, so now I'm going to say, let's see, my t-score, I'm going to calculate a t-score because it's a sample, right? My t-score is going to be equal to the x bar minus the mean, right, for the entire population, divided by the standard error. What's my standard error? My standard error is going to be equal to, that's going to be equal to my standard deviation divided by the square root of my sample size, which is 5. Here's my standard error. Let's calculate what t is. T is equal to, my standard error, the difference between x bar and, let's see, x bar is 5.3 minus, what was the mean? The mean was 4.5 equals 5 minus, whoops, I'm going to escape that. So t is equal to 5, right, minus 4.5. Right, I'm going to put that into parentheses, divided by the standard error. How many standard errors apart are these two values? Turns out that my t-score, t is equal to 2.5, right? Now, in order to know whether I can reject the null hypothesis, I have to find out what the critical value of t is at alpha is equal to 0.05 for 4 degrees of freedom, and at 0.01 for 4 degrees of freedom. Okay, so let's go to our t-table. Why did I do 5 and not 5.3? Did I do 5? Did I do 5? Oh, you're right. Excuse me. 5.3. I made a mistake. T is equal to 4. That changes things enormously. Okay, so let's take a look at what the value. Thank you for catching that error. You're absolutely right. Okay, so let's go to a t table, a t distribution table. So for 4 degrees of freedom, for alpha is equal to 5%, I'm working with my 95% confidence interval, 2.5%. It's two-sided test, 2.5% each tail. So I'm working with this column. Okay, so for 4 degrees of freedom, my critical value is 2.7. For 4 degrees of freedom, at 99% of alpha is equal to 0.01, 0.005 on either side, my critical value is 4.6. 2.7 and 4.6. So let's see. Where's my calculation? Where'd Excel go? Let me find Excel here. 2.7 and 4.6. Where'd it go? Here it is. 2.7. So let's see. T critical, okay, for alpha 0.05 is 2.7. T critical for alpha, in other words, a much more strenuous test, alpha is 0.01, is equal to 4 point, I forget what it was, 4 point something, 4.7 was it? Something like that. I forget, but it's big. Okay, so now T critical is equal to 2.7, 4.7. So for the first question, I can reject the null hypothesis because at level 0.05, altitude 0.05, my T calculation exceeded my T critical for that 0.05. But I can't reject the null hypothesis for T critical is equal to 0.01. How did I know that it was double-sided? Let's see. Independent do the measurements provide sufficient evidence to reject the null hypothesis? Well, if I say mu is equal to 4.5, that's order. So if I give you that null hypothesis, you know that's a two-sided test because either being bigger or smaller is going to reject the null hypothesis. If I wanted this to be a one-sided test, I would have had to say mu zero is equal to or greater than 4.5, or mu zero is equal to or less than 4.5, with the alternative hypothesis being the other part, just greater than or just less than. So no, the null hypothesis was rejected for at a 0.05 level of confidence, alpha is equal to 0.05, because T critical, remember, let's go back here. The T value I calculated, T is equal to 4, right, in my calculation. These are 4 standard deviations apart. A T critical was 2.7 at 0.05 from the table. So I don't exceed T critical, so I fail to reject the null hypothesis. Oh, excuse me, I do exceed the T critical at 0.05 because it turned out to be 4, bigger than the T critical, 2.7. But at 0.01 level of confidence, alpha is 0.01, T critical for 4 degrees of freedom is 4.7. And in this case, I don't exceed that 4.7, so I fail to reject the null hypothesis. First part, I do reject the null hypothesis. Second part, I fail to reject the null hypothesis. Okay? That makes sense. That was the last problem. Okay, so we've been going for a long time now, and I'm starting to lose my voice. So what happened? We just did number 15, didn't we? Just did number 15. Number 15, that's regulated, tested. Well, that's the only difference there between 14 and 15 is that 15 is a one-sided test, right? So it's a different t-value than 14. If we were, I'm going to pull up the t-table again. You do them exactly the same way. T is equal to x bar minus mu over the standard error, and you get a t-value. Then you compare it to t critical. And if I pull up the t-table, if I pull up the t-table, for a two-sided test at a alpha is 5%, the t critical is going to be in this column. For a one-sided test, all 5, notice that 5% is, even though I say alpha is 5%, 95% confidence, right? In other words, 5%, 95% confidence kind of goes along with 5% chance of being wrong, right? So you notice that under T, it says that it's for T for 0.025 in the tail, in either tail. It says right tail, but it's either tail, 2.5%. This is half the alpha. This shows half the alpha. So in a two-sided test, we allot 2.5% chance of error below on the low side and 2.5 chance of error on the high side to account for 5% chance of error. When we're talking about a one-sided test, all 5% goes to one tail, right? So we're looking at this value here, where we're only looking at one tail being 5%, not two tails being 5%. So if alpha is equal to 0.05 for a one-tail test, I use this column. If alpha is equal to 0.05 for a two-tail test, I use this column. So I get different values of t. So I get different chances to decide whether or not the value of t I calculated exceeds the critical value of t to let me reject the null hypothesis.